Good morning, folks. Got you a nice problem to start off with today. So dive into that. It's a little bit of a review, essentially, but we've been looking at graphing rational functions. So solving rational equations is a good thing to remind us how to do nicely. So give that a shot and we'll talk about it. So any thoughts or suggestions on what how you want to start? What you want to do first?
Well, I'll probably get that all the what's the word? Coefficients on one side, not coefficients.
Oh, terms?
Yeah, terms. There you go. Words are escaping me this morning.
So we could set it equal to 0 first. That would be perfectly fine. I'm not averse to doing that. We could make that a subtraction. Oops. And then equals 0. So yeah, that's not a bad thing to do at all. What do you not like about this problem?
Love this problem. It's nice and easy.
It has some nice pieces to it. The fact that p plus 4 and p minus 4 are the factors of p squared minus 16 is nice.
Yeah, it means you don't have to have trinomials on the bottom.
Yeah. Why would you have trinomials on the bottom? You're not
Well, not necessarily trinomials, but if you had, say, this p squared minus 16 didn't have any of the factors of the other ones, then you'd have three factored sections to multiply across everything.
True.
So you'd be multiplying like 5p times, like say that was like p minus 3 and p plus 2 with the other ones, then you'd be multiplying, three different terms against 5p, and you'd end up with like a fourth degree polynomial.
So the fact that that's a nice and factorable into the pieces we have, you're absolutely right, does mean to clear that out, all we have to do is multiply by the p squared minus 16. And we could have done that before or after subtracting the 1 minus p over 4. So either order would have worked.
Wait a second. Why are we doing that? I'm sorry.
Well, I don't like the denominators.
Okay.
And if we multiply by p squared minus 16, that p squared minus 16 will cancel, right?
Mm-hmm.
When it distributes to here, the p plus 4 is inside the p squared minus 16. So that p plus 4 is going to cancel with the p plus 4 in p squared minus 16, leaving just that times the p minus 4. And when it distributes here, it's going to cancel with the p minus 4, leaving just the p plus 4.
Okay.
Essentially, the good old clearing fractions. Instead of clearing fractions with numbers, we're clearing fractions with expressions. Which is why, as Andrew said, it's really nice that the p plus 4 and p minus 4 are the factors that made up the p squared minus 16, because if not, we'd have to multiply by a lot more. So we get a nice 5p minus 8 times the p minus 4 minus 1 times the p plus 4 equal to still 0, which is nice. One of the reasons we like having things at equal to 0, because we can multiply by whatever we want. And as soon as we get rid of those fractions like we did, it turns into generally a nice little problem. What's that, negative 4p plus 28? Seven equals 4. That's a weird thing to write. And as long as that 7 isn't a domain restriction for the problem, it's a solution. Our domain restrictions for the problem would be negative 4 and positive 4, because that would have made these denominators equal to 0. So that 7 isn't a positive or negative 4. So that's a solution. You guys like that one? You want to try another one like that? I'm going to take that as a yes. We'd love to. Unless you guys nodded or shook your head. I couldn't see you at that moment. So I'll give you a couple of minutes to try that one. So Andrew, I'm going to clear out those denominators before setting it equal to 0, but either order is fine.
It's just a habit
Yeah.
from math. I think math 65. I
65 and 95 tends to cause that habit. Yeah.
I just like to have everything on one side first, because then you're multiplying by 0 and you don't have to worry about it. It just goes away.
Yeah. And that's perfectly reasonable. But to have our denominators cancel, we're going to need to be multiplying by an x plus 1. So we're going to be multiplying by an x plus 1. We need to be multiplying by a 2, so that 2 cancels. And we need to be multiplying by a 3x plus 3, but 3x plus 3 is 3 times x plus 1, and we're already multiplying by x plus 1. So all we need is that other 3. So that's our, what we'd call the least common multiple of our denominators. So that's what we're going to multiply by.
So can we just change that to a 6?
Absolutely.
Gotcha. I want to make sure before I did it.
And if you want, depending on what part of it's, making sense, what part of it you want to work on visualizing, we got 6x plus 1. That's being multiplied by the 6 over x plus 1. Then we have our 6 times x plus 1 times the 3 halves. And then that's going to be equal to the 6 times x plus 1 times 2 over 3x plus 3. Now we could multiply all that together and then try to reduce, but the whole point of multiplying by the 6 times x plus 1 was to get these to cancel. So we're going to take advantage of that and make them cancel. That's going to cancel with the x plus 1 and the 3. So I often don't write that complete step out because the goal was to have those things cancel. So just canceling them out immediately is nice. But if you want to see the whole thing, write it out, but don't multiply all that stuff together. Your goal is to get stuff to cancel. So take advantage of the canceling. So we'll have 36 minus 9 times the x plus 1 equals 4? So that clearing step, it's a big step. There's a lot going on. We got to multiply by the right thing. We got to make sure we cancel everything out nicely. But gosh, it leaves us with a nice problem to finish off with. (36 minus 9, x minus 9 equals 4. So what, 27 minus 9x? And again, as long as that's not a domain restriction, that's our answer. Our only domain restriction was -1. both of those, -1 would make 0. So as long as we don't claim that -1 is an answer, that does happen sometimes. It's pretty rare, but it does happen sometimes that your domain restriction ends up being your answer, in which case there's just no solution. Anybody horribly uncomfortable with any part of that? Crystal, this is not the happiest I've seen you.
I went through the problem myself, and then I'm looking at yours, and it's very different. So I'm just trying to follow what you did. So somewhere between the second red line is where I'm like, wait, what? But I'm computing in my brain right now.
Fair.
There's like, I've seen these kind of problems done like 3 or 4 different ways. So
Yeah.
that's the hard part, is everybody has a different way to do it that works for them.
Mm-hmm.
Like for me, at least, I have to write out visually everything, because if I don't write it all out, then I'll lose something.
Yeah.
I can't skip steps like Mr. Hogan is. Just, let me just skip that little section because I already know what it's going to do. I can't do that. Then I'll leave something out.
Like here, I didn't write out. I kind of did all the cancelings up here because, those were going to happen. So nice. Here, I tried to write out a little bit more. But there's still a lot going on, and that's the thing with this clearing. It is a big step with lots of little pieces, but man, it leaves us with a nice thing to solve.
Well, and that's the thing too, is like, so like the upper part, like I wrote that whole section out, but because I moved everything to one side with the zeros, once you get this 36 minus 9x minus 9 equals 4 or whatever, minus 4. So I just combine all the terms. So I skip like 3 of these steps where I'm just at negative 9x equals 23.
Frankly, if you you turn that into a negative and say equals 0, turn that into a negative and say equals 0, turn that into a negative equals 0.
Yeah, and then I just combine everything in one step.
It's, I argue, like, is it any less steps?
Well, I don't like, I already combined on, like, with this 36 minus 9x minus 9 minus 4.
Uh-huh.
I immediately just wrote down 23 minus 9x. So, like, so I just skipped, like, one step there because I already knew all the terms. I just added them up in my head and scratched them out as I add them.
Yep.
That's about the only thing I can do in my head without screwing it up. It's combining like terms.
And I always do want to encourage you guys to find your own flow through these problems. But at the same time, you'll often see people with a problem like this where instead of using this least common multiple to destroy all these denominators, they'll build up common denominators in everything and bring everything together. And that's a very disadvantageous path because it's a lot more computation, it's a lot more work, it's a lot of places to make errors. So, variations in how you set it up and how you path, through it are good, but you want to be using the tools that make it, as long as you're also still using the tools that make them, fairly nice and easy to handle. Okay. Questions about either of those before we kind of, start making it a little bit weirder?
Oh, joy.
Oh, joy.
I can't wait.
Well, the nice thing is you don't have to, because here it is. Let's say we've got a good old x to the third plus 6x. And we want to know where is that less than, or what we say less than or equal to, 5x squared minus 2. So why are we looking at an inequality instead? Well, inequalities come up a lot. We're not always wanting to know where things are the same. If we want to know where is, the power requirements for our system, less than the output power for the motor. We're often not looking for exactly when do things match up, but when are things in the range that we want. So inequalities are common for that. And polynomial and rational inequalities, with the tools that you guys have built up right now, are actually fairly easy for us to handle with just a couple of perspectives, not even new techniques or mechanics, just a certain perspective on them. So I'm interested to see, without any kind of preamble, what you guys would do if this suddenly became an inequality instead of an equation, and you were still asked to solve. Ooh, make this a +2, sorry.
I mean, wouldn't you do about the same process? But isn't it, if you like divide by a negative, you have to switch the greater than or equals to sign to the opposite?
Yep. If we multiply or divide by a negative number, we have to reverse the inequality. True. So when you say the same process as before, how would you start if it was the same process as before?
I don't know.
Well, to give you a good chance, Andrew, I'm going to ask you what you want to do first, because I'm hoping you follow your pattern. What do you want to do first, Andrew?
I mean, realistically, you could move, because you have x cubed and x squared, so you have a third degree and a second degree polynomial or a binomial, but they don't have all the makings to factor them down because they're missing degrees. So moving everything to one side of the inequality would be the first step, right?
Henry, get in here.
I think that would be a very nice first step. Absolutely.
And then you could follow that with synthetic division to break it down to a quadratic, correct?
Yeah. So I'm going to translate that, Justin, into you could try to factor it, right?
Yeah.
Or find its roots, or find its zeros, however you'd want to express that. So take a moment, do that.
At least this one, there's not a lot of terms that it could be.
Yeah. Oops. You haven't been using P over Q, using P over I. And Andrew, we certainly could still be missing terms if we subtracted everything over. And if we're missing a term, we just put a 0 in, right?
Yeah, I just on this one I noticed that the missing terms were on the opposite side of the inequality.
Yeah.
I hate it when you get down to like your quadratic and you're missing a term. So you got to put a 0 in your quadratic equation. Sometimes that makes it really funky.
In some ways, it can make it easier, but it does make it weird. It does make you feel like, uh-oh.
Yeah, well, it's just like sometimes I forget the plus or minus, like if it's missing the b term.
Yeah.
Because I'll forget to write plus or minus outside of the, square root.
Yeah.
And so then it's like, oh wait, and then I'll get down to the bottom, like, wait a second, this doesn't look right, and then I'll realize I've missed the plus or minus the whole way down.
That happens. So we could look at the graph, but there's only 4 here, so trying them isn't too crazy. But if you wanted to look at the graph, we could do that too. But I'm just gonna. There's only 4, so if that was a 1, that would be a 1 and a -4 and a -4 and a 2 and a 2. So that just works. That's nice. It's hard to argue with that. I just tried 1 because it's easy and nice if it works. So that means we've got x minus 1 times x squared minus 4x plus 2 is less than or equal to 0.
Well, I guess you can use -2 as well, because that's the one I used.
No, yeah. Well, the nice thing is, if that's true, then we could even do it here. -2, you said?
Yeah, I use -2.
1. That would be -2. That would be -6. That would be
I don't know about down there, but
Well, if it's a factor of the upper one, it should be the factor of the lower one as well.
the was it like -2 times 1, and then -5 plus -2 is -7, which would be 6 plus -7, which is -1, times -2 is 2.
Yeah, but that -7, -2 times -7 is 14.
Oh yeah, I moved one over. You're right. See, I'm too tired to be thinking.
That happens. So what about this x squared minus 4x plus 2? It doesn't look factorable, so quadratic formula, right? So that discriminant 16 minus 4 times 1 times 2 is 16 minus 8. So our discriminant is 8. So it's going to have some real solutions. So our x value opposite of b, so 4 plus or minus the square root of our discriminant over 2 times 1. So 4 plus or minus 2 square root of 2 over 2, or 2 plus or minus the square root of 2. So in trying to find our roots or zeros or x-intercepts, we found those 3. So zeros at x equals 1 and 2 plus or minus the square root of 2. Now, that's not the solution set to this problem. That's where the function is equal to 0. So actually, since we wanted less than or equal to, those are our equal to's. So they are 3 solutions to the problem. But it's an inequality. There are infinitely many solutions to this problem. And there's a couple different ways we could go about finding those. But the nicest one for us right now, I think, is to look at this thing's graph. Because we know what this graph looks like. whether we know it or not. We know it has an x-intercept at 1. We know it has an x-intercept at 2 plus the square root of 2. Square root of 2 is really roughly 1.4. So 2 plus 1.4 is 3.4-ish. So 1, 2, 3, 3.4. So right there, we're going to have our 2 plus the square root of 2. 2 minus the square root of 2, so 2 minus 1.4 is about 0.6. So there'll be another solution there at 2 minus the square root of 2. So we got 1 there, 1 there, and 1 there. Is that fair? And the last idea about, okay, how are we going to graph this is, do we know whether or not it's going to come up this way from the bottom through those intercepts, or if it's going to come down this way from the top and go through those intercepts? So which do you think, 1 or 2?
2. It's gonna go up through those intercepts because the leading coefficient is positive.
Yeah, we got a positive leading coefficient. So that means it's got to come generally upward. It's an odd degree, so it's going to go, from down here and then leave out that way, right? Our zeros all had multiplicities of 1, so they're all going to pass through. No bouncing happening here. So, okay, we don't know how high or low it goes, but that's generally how the function is going to look. And we are asked, where is this thing's function values less than or equal to 0? Where on this graph are our y values less than or equal to 0? From there to there, all those x values are giving us y values that are less than 0 because we're below the axis. This is one of the reasons, Andrew, it's really nice for inequalities to be set to 0. Because then instead of asking, above and below what, you're above and below something very easy to identify, our y-axis. Sorry, our x-axis.
That makes sense.
So for that range and for all the values between 1 and 2 plus the square root of 2, all those x values are giving us y values that are below the axis, y values that are less than 1. So our solution set, where is this less than or equal to 0? Well, any negative value all the way up to 2 minus the square root of 2. And since we can be equal, we're going to include that unioned with our set from our interval from 1 to 2 plus the square root of 2. And that's our solution set. So one of the reasons why not only do we want the kind of mechanics for solving these things, but one of the reasons we like to know what the graphs look like and how the graphs visually behave is they really do allow us to solve lots of things like inequalities. For those of you going into calculus, when you start doing integrals and particularly integrals, having a sense of how the graphs look and how the graph behaves will affect your setups and which mechanics you use when. So being comfortable with what that graph looks like is really super helpful.
So if that was just a less than inequality, these would be open parentheses, right, instead of brackets?
Yep.
Because the brackets just mean including that point, correct?
Correct.
I always have trouble with the brackets and the parentheses.
Now, we couldn't make this much stranger, could we?
I have faith in you. Pretty sure you can figure something out.
So rational inequality either take a moment and decide how you'd want to start approaching that and start doing that, or if you're thrown off by all this, see if you can form that into a question, and I'll see if I can help.
Try to have a thought process here.
All right. What's your thought process?
Can't you just multiply one side of the inequality by the denominator?
No, and I'll tell you why.
Well, both sides of the inequality, technically.
Still no. So very dangerous. The one thing with inequalities, as Justin mentioned, we do have one little caveat going on here. Let's say it was just like, oh, this instead, plus 2 less than, say, 1 over, just x plus 1. If this was an equation, you'd want to multiply both sides by x plus 1 and x plus 2, right? To get those things to cancel out. And totally, if that was an equation, yes, multiply by x plus 1 and x plus 2. But Justin mentioned the difference, the biggest difference in solving and manipulating inequalities. When we multiply or divide by a negative number, we have to reverse the inequality. So if you multiply both sides by x plus 1, is x plus 1 negative or positive?
Negative?
Sometimes x plus 1 is negative. Plus
So
1 is negative when x is negative 5.
I'm so confused.
Well,
So-
X is a variable. It could be anything.
So this, if we multiplied both sides by x plus 1, if what we're multiplying by is negative, then we're supposed to flip the inequality. If what we're multiplying by is positive, we're supposed to not flip the inequality. Well, x plus 1 is both positive and negative depending on what your value for x is. So do we flip the inequality or not?
I see your point.
So we can't do that with inequalities. So what we'd have to do instead is subtract it. No, come on. Work with me. Subtract it over and then combine this good old common denominator style and bring it all together. Inequalities ruin one of our best tools in that whole clearing idea because we don't know what to do with the sign.
They just both factor so nicely. It'd be convenient.
So because of all of that, even if we had a problem like that, we'd still have to move it all over, get common denominators, and we'd still end up with something that looks like this. Now, the nice thing about this is if we ignored the less than 0 for a minute, and we were just looking at that, it would be nice if we'd spent some time practicing on how to analyze rational functions like that, like being able to find things like asymptotes or intercepts or.
We did.
So could we graph that thing?
Yes.
And if we had a graph of that thing, whatever it looked like, could we tell where it's below the axis versus where it's above the axis?
Yes.
So where it's below the axis would be solutions, where it's above the axis, in this case, wouldn't be solutions. If it said greater than 0, then we'd want the ones above the axis and not the ones below. And that's why I said we really have all the tools for solving these. We just need to know we have them. Fair?
Yes. So would you want to factor that at all?
Well, yeah, because factoring that tells us where the vertical asymptotes are. It tells us where the x-intercepts are. So it tells us what the shape of that graph is going to be.
Right.
So your 5 and your 6, and they're both going to be negative. That's going to be a 9 and a 9. They're both going to be positive, right?
Yeah, because that's what I went straight to.
But what does that tell us? That tells us we have at 5 and 6, we've got x-intercepts. And at -9, we have an asymptote. It also tells us, since the degrees match, that we have a horizontal asymptote at 1. Is that fair? Now for this one, figuring out what the graph looks like is a little bit tricky, but I'm going to start all the way on the left here. Coming off of this end behavior, we certainly are forced to go upward, because if we went downward to be asymptotic to the -9, we'd need to have an x-intercept after or on the left of that -9, and we don't have one, so it does have to be up there. On the other side, most of the ones you've seen, if it comes, out this way, if it comes upward, the next one is going to come from down below. That's what most of the ones you've looked like or you've seen look like, right? It kind of goes up here and then passes, around the universe, whatever, and then comes up from this side. But I'm going to ask Aaron, because you usually like these. Aaron, what do you notice about that 0 at -9?
I don't know.
Well, it comes up twice, right? For our zeros, that kind of multiplicity meant it bounced off our axis, right? The same thing actually happens with asymptotes. Instead of going up and out and through around, they'll go up and bounce off that infinity and come back down. Does that make sense? Now, what happens with this 5 and 6 is a little bit tougher, but we know that I don't have to match this asymptote until we get to our end behavior. So I'm not going to worry about that blue asymptote until we're out there. So we're almost going to ignore this asymptote for a bit and just worried about hitting our next intercept. We know we've got to cross through the axis at this 5 and nowhere else. So this thing has to come down through that 5. It's multiplicity 1, so it just slips right through. And we know we have to come up through that 6 and then end up asymptotic. And we know we have to pass through because those are multiplicity 1 x-intercepts. We know we can't pass through anywhere else because if we passed through anywhere else, we'd have an x-intercept there, and we don't. Now, we could also use signal. Go ahead.
How does that work? Because it's technically crossing the asymptote right there.
Who said you can't cross asymptotes?
Well, generally you don't because, right, isn't it approaching zero?
Is a very common and dangerous thing that people often think and or say. You ask people what an asymptote is and they'll say it's something that it's a line or something that you get approach, get close to, but can never touch.
Yeah. Well,
That's not true.
The never touch part is the part that makes you think that.
Yeah, but people say that, but it's not true. You can touch asymptotes. You can't touch vertical asymptotes because vertical asymptotes are where the function is undefined. But horizontal asymptotes, you can touch horizontal asymptotes all you want. We even saw problems yesterday where we had a graph that went, say, like that, and then like that, and then like that, right? It had that horizontal asymptote through whatever it was. I'm going to say it's just y equals 1, but it passed through that y equals 1 there, right? That's perfectly fine. In oscillation models, dampening oscillation models anyway, you often get oscillations that will, reduce down as time goes on. That y equals 0 there is an asymptote. It's approaching that as x goes off towards infinity. It passes through that asymptote over and over and over again. The only asymptotes you're never allowed to touch are vertical asymptotes because at vertical asymptotes, your function is undefined. Horizontal asymptotes, slant asymptotes, curve asymptotes, you can touch them all you want. They're just end behavior arguments. They tell us the behavior of the function as x increases without bound. It doesn't tell us what happens when x equals, -8 or whatever number that is. I have no idea.
So basically, like, as far as end behavior goes, then it can go on either side of the horizontal asymptote, but it can never actually equal 1.
No, it equals 1 right
Effectively.
there. There's some x value for which that equals 1. It's just as it goes off this way, it has to get closer and closer to that line.
Gotcha.
It can pass over it as it does that, but it has to stay in an ever shrinking distance from that line as it does it.
That makes everything way more confusing.
It is. And that's one of the reasons people like it gets close to but never touches, because that's nice and straightforward. But the fact that, it can touch it. The technical definition is, we'll get for any epsilon greater than 0, there exists a delta, there exists. It's very technical definition for what it means to be an asymptote. You'll talk more about it in calculus. But yeah, it's a little bit more dramatic than we approach it but never touch it. So we want to be okay with the fact that we can pass through our horizontal asymptotes if we need to. They just level off in the end behavior. So to finish up, because I know you guys have to go, where is this graph less than 0? It's only less than 0 for those values between 5 and 6. So the solution for this inequality is everything between 5 and 6, not including our zeros, so not not including 5 or 6. Fair? So again, as I said, for the section on inequalities, since we know what these graphs look like, or can decide what these graphs look like, we technically know all the tools necessary to solve these inequalities. And it's actually nice because it gives us a chance to practice those skills with some context. But it does take a little bit of perspective.
So all these inequalities are basically in relation to the x-axis, right?
Yes.
Like
What values
either-
for x make the function do stuff?
Gotcha. So basically, it's either above x or below x, and if it's below x, then it's less than 0.
And if we have it set equal to 0, yeah, and that's why we generally set these equal to 0, because then we can just look at the axis and tell.
Gotcha. So like so say we had like a quadratic equation that was all above the x-axis, then it would just be what?
Well, if we had, say, x squared plus, say, I don't know, make one up, 4x plus 9, where is that greater than 0? If we graph that, it would be all above the x-axis. So where is it greater than 0? Everywhere. So we'd have from negative infinity to positive infinity. If it said less than 0 instead, it's never less than 0. So there'd be no solution.
All right. I was just checking my own thought process there. Make sure I'm not fully retarded.
Not that I've noticed.
You should see me at about 5 minutes after I wake up.
I thought I did.
No, I usually get up like 30 minutes before class.
That's good.
If I don't, then I'd be over here looking like a zombie.
Okay, so any questions on that before you guys go play with that? So send me questions or ask each other on the forum questions about this stuff over the weekend. Let's see, I'm in service meetings all day tomorrow, so I'll be, if you send me questions tomorrow, it might be a little while before I get back to you because we got meetings, Zoom meetings. I'm not sure how they're going to make that work, but we'll see. But if there's any big things you want to look at, make sure on Monday you let me know so we can look at them. And have a wonderful weekend.
Thank you. Have a nice day.
I will. Thank you.